some point in time. So. And these are what's left of what there were. Okay, so today we're going to move into chapter 6, which we begin to start talking about estimation, estimating things that are unknown. A key element of that is sampling distributions. What is a sampling distribution of a random variable? What is a sampling distribution of a statistic? And then turning that into confidence intervals or other inferential statements about the population or the situation we don't know. Right? So there's one question about this current homework about problem 5, and it kind of fits in to this in a way that we'll see. So the problem 5, right, was this machine where that had 15 levels, and at each level a ball that's dropped right onto this thing either bounces left or right, and then into the next one it either goes left or right, and so on until it keeps going down. And there could be a 50% chance for left or right, depending on where it goes, and then ultimately it's going to land in some bins down there. Right? And so it asks, well, what are the chances that it ends up in different spaces, right? And so this is closely related to, which distribution is this related to that we've looked at? Binomial, right? So it's related to binomial. If there's 15 levels, each level is kind of a trial. You know, if it hits one of those, it's kind of a 50-50 chance of going either way. So there's 15 levels, and the chance of going left or right, if this is constructed well, is supposed to be about 0.5. So what is so if we call x the number of times that it goes left, right? Well, that will be, so that thing will be binomial, distributed in a binomial random variable with n equals 15 and p equals 0.5. Or let's say that the number of times that it goes right. That will make the picture look a little bit. You can do it either way, left or right. But if it always goes right, if it goes right 15 times, it ends up in this last bin over here. If it goes left 15 times, so right 0, right, it ends up in this bin way over here. And so all the places in between are different outcomes, really, under this binomial model. 1, 2, 3, right, etc. And the book has it like at 0, plus or minus 1, plus or minus 2, but it maps into those probabilities. Right? So if this is the binomial, what, x can take values 0, 1, 2, 15. So what are the probabilities? What's the probability that x equals one of these little values? Is just simply the binomial formula. So in general, if n choose x, p to the x, 1 minus p to the n minus x. In this case, it's 15 choose x, because there's 15 levels. And if it's 1/2, and if these things are both 1/2, it simplifies, 1/2 to the n, 1/2 to the 15th, actually. If it's 1/2 and it's 1/2, you can add those exponents, and there's x, and 15 minus x, and it just becomes 15. So those are the probabilities that it ends up in each of these 16 different spots, 0, 0 to 15. But as you get these larger sample sizes, more and more levels, right, it starts to look pretty continuous, right? There's a lot of possible values in here that can happen. And that shape actually starts to look like that, looks like a bell-shaped curve. Right? So what's the average? Right? If you needed to approximate that distribution, we need to figure out the average and standard deviation. Because the normal, everything's based on average and standard deviation. So for this number here, right, what's the average? the average number of steps to the right?
7.5.
7.5, right? So 15. In the formula, it's n times p, so 15 times 0.5, or 7.5. On average, it's going to go 7.5 steps to the right, 7.5 steps to the left, and on average, it's going to end up right in the middle. And what's the standard deviation of the number of steps to the right? Well, that formula was n times p times 1 minus p. You can square root of all that. So n times p times 1/2 again is 3.75, and the square root of that. So that's a little bit more than 2. I mean, a little bit less than 2, kind of at the standard deviation. So if you calculated the chances under a binomial, actually adding up binomial probabilities versus areas under a normal curve, it's going to end up being kind of close. Right. What did you think about the simulation part of it, running that R code? Right? Which values of n, what sample sizes produce better normal looking curves? Yeah.
25 and then 15.
And then 5 was very discrete, right?
Yeah.
Just a few points, right? Right. So as you get bigger, the distribution of x there becomes much more bell-shaped. Right? Yep. And so that ties into what we're really doing here with the sampling distributions. And so a sampling distribution is a probability distribution of a statistic. And a statistic is some numerical summary of our data. So in this binomial case, we really have 15 different random variables that we record, left or right at each level. So we really have 1, 2, 3. We really have 15 different things that could be, left, right, left at the end. We really have 15 different things that we've recorded. And we translate that all into, right, x equals the number of steps to the right. So x can have values 0, 1, 2, up to 15. And so the probability distribution for that one is this binomial we've been talking about. So x, counting the number of steps right, is a statistic, and it has a probability distribution. It has probabilities, it has a mean, it has a standard deviation. Right? And that's an essential concept that we're going to look at. Right? So the coins, or this 50-50 things, is pretty reasonable to think about. But what about flipping pigs? Right? The next thing we're going to do is look at our little pigs here, right, and talk about doing things to them, recording things on flips of them, and summarizing a probability distribution. But any questions on back here on the homework part of that one? Right. So when you have something that's a little bit more unknown like this, like these pigs, and you throw them, they can land a bunch of different ways. What do you think would be an interesting way to record? What should we, let's flip them a few times. Say, what do you want to do, like 8 times? 10 times? Maybe we can do 10 times. Let's do 10 flips. And what statistic do you want to create out of this? What do you want to count? Yeah.
How many times it been on speed?
On its feet, right? So on its feet. Can you record 2 things at once? So on its feet versus
No, on its feet.
not on its feet. So on its back or on its side, or some things are really rare. Like it can like land and be kind of balanced like that, but that's not going to happen too often, and you get a lot of zeros if you did it that way. It can kind of balance on its sitting on its butt, standing up. Doesn't happen that often. So on its feet, or maybe feet up in the air, or something like that. So if you flip it 10 times, can you record those two things at once? Like each time you recorded it either on his feet or his feet in the air or something else. Right? So flip it 10 times and record how many times you get one of those. It's easiest to kind of mark that down. So. Oh, sorry. Anybody else not get it? Not get it. If you've done this, what did you get them both? What did you get for?
2 on his feet, and then 4 when they're in the air.
4 in the air. Okay. Yeah.
1 on its feet and 5.
5. Yeah.
1 on its feet, 3 in the air.
Okay. Yeah. You do?
Yeah, one on its feet and 4 in the air.
4. I'm gonna make these go down. A little more space going down. Right. Yes.
1 on his feet and 4 in the air.
5 in the air. Okay. Yeah.
1 on its feet and 4 in the air.
4 in the air.
1 on its feet, 4 in the air.
Yeah. Okay, so we're gonna run out of space. So 0, 1, 2, 3. So 1, 2, 3, 4, 5, and a 2. 1, 2, 3, 4, 5. I think I need to record yours and a 2. And you said 4 in the air, and I wrote that up, right? So we'll see how that goes. Yeah.
I have 0 on its feet and then 2 in the air.
And 2 in the air. 2.
2 on its feet, 0 in the air.
0 in the air. Okay. Yeah. Okay. 2.
Yeah, I think I got 2 on its feet, 2 in the air.
Okay. And 2 in the air.
0 on its feet and 7 in the air.
7 in the air.
I got 1 on its feet and 3 in the air.
Yeah, 1 on its feet and 1 in the air.
Okay.
I
Yeah.
got 0 on its feet and 2 in the air.
2 in the air.
1 and 1.
1 and 1.
1 on its feet and 4 in the air.
Did you say 1?
Yeah.
And 4 in the air. Yeah.
2 and 2.
2 and 2.
0, 3.
0 and 3. Yeah.
0.
0. Okay. Right, so we have 2 different outcomes. These are 2 different variables. Maybe this is X and this is Y, if we wanted to call it letter names, right? And they have distribution. So out of 10 flips, we have probabilities. This is kind of showing you what they are. How do these 2 random variables, these 2 statistics, how do they differ? This is a lot lower, a lot more probability at 0, 1, 2. Not much. We could get 3, we could get 4. I mean, if you did this 10,000 times, you'd probably get some of these larger numbers, right? But this one looks like it's going to average, 3.5, something like that, in terms of feet in the air. Maybe more standard deviation. It went all the way from 0 to 7. This one's going to have smaller standard deviation. So all these summaries, right, are statistics. And each statistic, depending on how you're sampling it and doing it, has a probability distribution. And that's a key thing to understand as we want to talk about, well, what were the probabilities of getting these in reality, not just in our 20 samples or so. Well, mine was 0 and 4. So yeah, so you're in line with that, right? So the general perspective we have with this is we have a population. And it has certain characteristics. So our population, and we would like to have, know the entire population. We'd like to be able to take a census of birds and see how many eggs they're laying. We'd like to take a census of people and know their health status. Or we'd like to have very, very, very large sizes and do an experiment to test one treatment versus another. Often these characteristics are described by parameters that we would like to know. So mu is the parameter that's often used for population average or mean. Sigma is often used for the population standard deviation. Just a simple P for the population proportion. And in general, those things aren't known to us. There are things more like flipping the pigs, where we don't know how the physics of it, how it's going to turn out, and we don't have enough experience to say that it's 50-50, like like flipping coins or something, right? And then we're going to take a sample, and on that sample we'll record data, and those might be called x1, x2. A sample of size n, we're going to have in measurements. So in that pig example, we did it 10 times, so you got a sample of size 10. And based on that sample, we can calculate statistics. So functions of our data, summaries of our data. So statistics are these summaries of data. And so x bar is the sample mean. There. Or what we call S, sample standard deviation. Calculated for the values. Or P hat is, P with a little hat on, little accent on it is the usual symbol for the sample proportion. So the fraction of times that you'd be stepping left or stepping right, depending on what you're, the fraction of times that the pig would be standing up or bouncing on its nose. And in these things, if we think about random sampling from this population, they have sampling distributions. They have probability distributions that reflect the population and also the sampling process. And our goal in statistical inference is based on one sample, is to go from these sample data and the statistics back up to saying something about the population, right? And that's the process of inference. So often we can just take our sample average or sample standard deviation. That becomes an estimate of that unknown population parameter. But in statistical inference, we also want to reflect uncertainty. Right? And so to do that, we think about the margin of error or the standard error. That is, we think about what does the sampling distribution of these things look like? How uncertain are they? Is x bar really close to mu in probability, or could it be more spread out? Right? So in that process, we're interested in the statistical side of this inference. And the key to doing these things is thinking about sampling distributions that we're doing today. So in general, if you have a larger sample size, you can say a little bit more about the sampling distribution, right? Like that the larger sample size is for binomial, it looks more normal. Right? And we have kind of a way of, mean and variance for those, but we'll kind of look at other things. So, just to illustrate things like sampling distribution, we're going to look at a computer application that involves some measures of ozone in New York City, and the distribution of values is actually quite skewed. Right? And we're going to imagine taking a sample of size 10 and then reporting the average. Our goal in this study would be to know what's kind of the average ozone measurement. And we're going to contrast that to taking a sample of size 40. Taking a larger sample of days to take that. Well, average from a sample size 10 from a large population, it has its own average. Right? What would be the typical value of X bar? And it has its variability. And in general, the values of X bar are based on 10 observations. They're going to be centered kind of about the same center value of this. As we'll see in the simulation, there's still a little bit of a tail there, but they're more reduced. Right? When we pick 10 from that population, we don't get as much variability. Right? We get some large ones, we get some small ones. You average them together, and the big and the small kind of cancel each other out in the sense of being away from the center, and it's more moderate. And the distribution of X bar is more bell-shaped. Maybe this is a little bit too extreme, maybe kind of still is, there's a few big ones out there. If you get a big one in a sample size 10, it pulls it up and makes it a little bit more extreme. On the other hand, if you took a sample of size 40, right, we've changed the sampling process to include more data. Now we're doing the sample of that. Well, the average is still going to be about the same as those other ones, but it's going to be more bell-shaped, it's going to be narrower, because there's a greater propensity for the small and the large to cancel out, and the average of those to be much more closer to the population value. So that's our population, and this is mu. Our sampling distribution here is going to be near the mu, right? And so the sampling distributions, these are illustrations of sampling distributions. Of X bar with different sizes. And so one critical thing we're going to think about with inference and making confidence intervals is what's the standard deviation of that sampling distribution? Right. How far do we go out here to get typical values? What's kind of this range? Not the minimum value or the maximum value, what's kind of the 95% typical range there, right? And so a standard error is really the standard deviation of a sampling distribution. And so in that picture, right, if this is do the normalish one, so like that X bar 10 picture, I do something kind of like this. And here's mu. Kind of the mu plus or minus a couple standard, mu minus a couple standard errors up to the mean plus a couple standard errors. SE is going to stand for standard error. Is going to be about 95% of the interval, right? It's going to cover most of the range under that sampling distribution. So the sampling distribution is illustrated right there. For the case of X bar, distribution of X bar. Right? That on average, the expected value of X bar is the population mean. And on average, the sample average should be, centered on that. And the variance of X bar should be something like if the xi's, if all of our measurements are independent of one another, then the variance of X bar was like the variance of an individual measurement, but divided by n, as we're averaging more things together. So for X bar, the standard deviation of X bar is the square root of that thing, because square root of variance. So the square root of that thing is like sigma, the standard deviation of one measurement divided by the square root of n. And that's the standard error that describes the variability for an average. It's variability for an individual observation, but it decreases. So, the kind of third part with this is that X bar on average is around what we would expect, what we would hope it would be. Standard error is decreasing at a rate of square root of n. And as you get larger and larger samples by the central limit theorem, the sampling distribution of X bar is approximately normal. So, by the central limit theorem, sampling distribution of X bar is approximately normal. It's centered at mu with a standard deviation of square sigma over the square root of n. And so for our sample average, we know a lot about what that sampling distribution looked like, right? For the pigs, we had to simulate it, right? And we got kind of one that was skew, centered at 0, 1, 2, with a few other values. For having the feet up in the air, it was more around 3.5 with a bigger range. Those, we had no idea, right? And they were what they were. But if you're taking in averages from a whole bunch of measurements, it ends up being close to normal. So let's look at one example on the computer. Does everybody have a copy of the handout? Right, so this will show you a little bit about this data. Let's see. So the air quality is a data set that comes with R. This data set has a bunch of variables: ozone, solar radiation, wind, etc. That is measured. So the first air quality, the first three rows of air quality are values. There's values for ozone, solar radiation, wind, temperature, etc. So ozone up in the upper atmosphere is a good thing. That blocks out UV rays that can be damaging to private. Ozone at the ground level is not good. It's caused in cities particularly where there's a combination of high heat, sunlight, and then the result of combustion engines. So the stuff that comes out of cars. That can react and create this ozone there, which is not good. It's damaging for lungs and eyes and things like that. Right? So to do these, I'm going to do this little command to attach this so I can reference the variable names directly. So the ozone values are skewed. Right? That a lot of them are small, safe ranges, but then there's some days that produce bigger ones. Right? And the mean ozone, if we had all the data, would be here. Right? And now we're going to imagine taking samples of different sizes from these 153 observations. Right? When I made this handout, I set a random number seed, and so this should reproduce the same numbers there. When I sample here, this little command here will give me 10 ozone values without replacement. So if I run that. There's some missing values in there that are kind of a little thing, but we're kind of not do too much with that right now. But it picked 10 values. 23 shows up twice there, but those are actually different 23s. It was 23 on different days, so it happened to pick them there. And if I take the average of a sample of ozone values, it's going to give me an average. So the actual average mean of, the actual mean of these ozone values, and I need to do this extra little thing to get rid of the missing values, is about 42. In this one particular sample, I got about 34. So my one sample value is a little bit low by the population. Right? But we're looking at the sampling distribution. What would be the range of values that would, so this little loop here is initially I'm going to set up this X bar vector. It's going to have 15 zeros to begin with. Right? Then I'm going to go through 15 times and replace each of those values by an average. So I'm going to take, it's a little loop, it's a little program in R. We'll go through something 15 times. I increments, begins at 1, then becomes 2, then 3 up to 15. And in the ith spot of that vector, I'm going to replace the thing by an average from a sample. So I'm going to get 15 different samples. This dot chart is one way to look at these things. So the first sample had an average of 55. There's another sample of average 33 or so. So if you project these things down, you see the samples range from about 23 up to about 53. 42 or so is the average, so there's a lot of things in that. That's one picture. A histogram is another picture of where these values would be. So that's just 15 samples. So that represents the sampling distribution of X bar in a way, but I can easily do, say, 1,000. Right? So I'm going to take 1,000 samples and show you the histogram of 1,000 different samples. Right? Now the original ozone looked like this, right? It ranged 0 to 200 or so, right? Pretty skewed. Now I'm taking samples of size 10. Right? And my samples of size 10, they're about the same average. Right? I can go find that baby line thing and add a little line here. There's the population average. And now my sample averages are around that. Right? So the sampling distribution of X bar is actually shown by this graph, right? It's not all 10 to the 15th possible samples, because there's a huge number of samples that could be happening. But this is based on 1,000 of them. Right? And so the standard error should describe the variability here. So it looks like about 42, if this is up to, say 72. 42 to 72 is a distance of about 30, so twice the standard error. So that means the standard error is about 15. Right, for that. And if we do the standard deviation of ozone in the population, that's like the sigma. I need to do this one little extra thing. That's about 32, but if I put it by the square root of 10, it's about 10. Right? And so if I thought it was, maybe I thought it would be a little bit bigger than that, but anyways, it's kind of on that magnitude as a standard error. We could redo this, not with a sample size 10, with a sample size, say 40. What the impact is on this sampling distribution do you think is going to happen when we go up to 40? Yeah.
It's going to be more accurate.
It's going to be more accurate. So what do you mean by more accurate?
It's more accurate.
So still centered around here.
Become more normal.
It's going to be a little bit, yeah, this one kind of has a little bit of more of a tail out there. That's kind of a remnant of the fact that the ozone values themselves were skewed. And I'm just, averaging 10, so it's not, it lessens that impact, but not totally. Right? Right? But if we get, the distribution of X bar should still be centered around that red line. It should be actually right in the middle still, right? But the standard error, like sigma over the square root of n, instead of dividing by square root of 10, you divide by the square root of 40. So the standard error should go down, right? A lot more. And so the way I made that graph, I reset the random number. That's the first part again. So here, that's still 10, so I don't want that. Did I do it? In here, I don't have that code in here. But this code is not too hard to change. Right, so I'm going to do 40 of these things with 1,000 times. Right. And I'm going to go through all my 1,000 times. And I'm calling this thing with 40. I'm going to sample 40 there. I don't want to do that little dot chart thing. Get rid of that. And then I'll do my histogram. I don't want that's X bar 40. Change the label. Right. So that's changing the code. Right. So set it up. Now I go through this loop. Take 1,000 samples of size 40, 1,000 different samples, and there's the histogram. And this AB line. And, oops, I don't need that. There it is. There's the red line. So it's still right in the middle, but because it's based on 40 instead of 10, the average is much more, the standard error is much smaller, right? The standard error before, using the S over the square root of n1 was 10. If we put 40 in here, it's about 5. About half as much. So the distribution is more narrow. So based on 40, this would suggest that our X bars are going to be more accurate. Right? So we're going to turn this into a confidence interval. Any questions about this type of simulation? The numerical thing that's happening in here is n equals 10. Then the standard error of X bar was sigma over the square root of 10. So if this is 32 over the square root of 10, you would have that number. If n equals 40, the standard error of X bar was sigma over the square root of 40. Well, the square root of 40 is the square root of 4 times 10. And you can break that up. So it's the square root of 4 times the square root of 10. And the square root of 4 is 2. So this one, that value is a 2 out here. So it's half as much. The standard error is half as much. So if the sigma is 32, to plug in that number, you would get the final calculation. But it's half as much as when you had n equals 10. So the standard error goes down with larger sample size, but not that rapidly. Right? To cut it in half and make it half as wide, you got to multiply sample size by 4. If you wanted to cut it in half again, you have to multiply it by 4 again. And so it gets increasingly expensive to make things nice and narrow. Right? But we're going to turn this then into a confidence interval. Right? The idea of a confidence interval is we have our estimate plus or minus some range. Right? And that's going to be based on standard error. So we want to do a confidence interval. Or got this somehow. Okay, confidence interval for the population mean. Mu. Right? So this application, that average over across a range of days. So our interval is going to be X bar plus or minus 2 times the standard error. And this plus or minus means, X bar minus 2 times the standard error up to X bar plus 2 times the standard error. Making an interval that way. Right? So the accuracy of X bar was around the mean, plus or minus a couple of standard errors. So now we want to go the other way and say, okay, we know X bar, we got our data. We have our one sample and our average. We want to make a statement about where do we think mu was? What was the average in the population? We've only seen 10 or 40 observations. The way we do it is to take twice the standard error and either add or subtract that from the mean to get this interval. Right? So this type of number 2, right, is related to normal. Related to the normal curve. And so under a normal curve, approximately, so for a standard normal, approximately plus or minus 2 has about 95% in the middle for a standard normal. For the distribution of X bar, it's centered around mu, and then mu plus 2 standard errors versus mu minus 2 standard errors gives the same 95%. It's not actually exactly 2 for the normal, it's more like, it's really 1.96 instead of 2. So some places will present it as X bar plus or minus 1.96 standard errors. That's fine, you know, if you know standard deviation. But it's about 2. Right? I think it's just conceptually, you take if the spread is about plus or minus 2 standard deviations, we replicate that in our confidence intervals. And so if you have a formula for X bar, it would be this sigma over square root of n. We'll get at that some other ways, right? And talk about that as we go forward, different variations of how would you know that or how would you get at that, right? Because mostly we really don't know sigma, we don't know what the population variance is. After all, we're doing this because we don't know what the average is. Probably don't know the variance either. In some engineering process things, you might have a variance from a previous time or a variance that you might be willing to use. But in a lot of cases, we're going to just estimate that from data, as we'll talk about as we go forward. Right? But what we would do with this interval, let's do one numerical example. Let's do a 95% confidence interval for average ozone. Let's do first a sample of size 10 and see what we get. Right. Put new numbers into this. So it's up here and then up here. So the standard deviation of the ozone, and I need to just remove these little extra thing to deal with it. This thing is, if we're doing 10 observations, our standard error is going to be 10.3. And let's take a sample from ozone of size 10, replacement equals false, so it's a simple random sample without repeating values. And I need to tell it to not do that. I get an average of 38.5. Right? So now my X bar is 38.5, my standard error is 38.6 and 10.3, 10.4. So X bar in my sample is 38.6. Right. Standard error that I'm going to use right now is reported as 10.4. And so my 95% confidence interval for the average ozone is going to be my 38.6 minus 10 times 10.4 up to 38.6 plus 2 times 10.4. And so that's 38.6 minus 20.8 up to 38.6 plus 20.8. So 59.4, and this one is 18, but 17.8. I think that's parts per million in the atmosphere for ozone. get a unit there. So that'd be 95% confidence about where the average is, right? The average was about 42. So this interval works. This interval covers the real value in all those measurements, right? Those large. But it's pretty wide, not too precise. 10 observations, you know, it's not very big. And so naturally the standard error reflects that. But you could get things that are 10 or 20 units away from the average, some averages, just by random chance. Most of them will be close, plus or minus 5, plus or minus 10, you know, closer. But every once in a while, you're going to get some that are out there. And the idea that we're dealing with, or trying to do, the procedure, the property we want our procedure to have, is that we don't miss that much. Right? We want it to be narrow, but we don't want to miss. We want our intervals to hit and cover the real value at least 95% of the time. And that's this idea of confidence, that we don't know for sure if it worked, but we want to feel confident that we're doing something that works most of the time. Right. And 95% is usually the standard that's used. Some government work uses 90% for some reason, but you know, it's if we had 40, right, we'd get another X bar. Now our standard error, this was, you know, the sigma over the square root of 10, right? The standard error in this case is our sigma over the square root of 40. So I know it's going to be half as much. And I know that it's, instead of being 10.4, that the standard error is going to be half as big because I've quadrupled sample size. But to make the confidence interval, actually you have to get a mean. So let's just take a quick sample here. So a mean of, I can verify this if I divide by 40. 5.2 is what I get if I take a sample of size 40. This time I got 51. So I got it a little bit on the high side. 51.0 as an average value of X bar. So 51.0. That's what I said, right? So now my confidence interval based on this different sample, right? 51 minus 2 times 5.2 up to 51 plus 2 times 5.2. So 51 minus 10.4, 51 plus 10.4. So it's narrower, not totally narrow. So that's 50, so 40, 40.6, hard to know. So that would be my 95% confidence interval. It still covers the 42. It's a little bit shifted off, just by random chance. Every once in a while you'll get something that's a little bit off, but it still covers. Right, so the idea is, what do we mean by 95% confidence? So we want 95% of our intervals we make this way to actually capture the true value of the population average. So if this is the average, this is the population mean. We get one sample, and we get a value of X bar, and then we put an interval on it based on the standard error. Right? And an interval is good, right? It does what we hope it does, if it covers the mean. And a lot of the times, you know, we set this up based on the standard error of X bar, that we would think that it would work out pretty well. Every once in a while, though, we'll get an X bar just by chance, right? That's going to be a little bit big, right? Or one that's going to be a little bit small, and it's just going to miss, right? So about 95%, 95 out of 100 intervals are supposed to cover. Right? But about 5 out of 100 don't. Just by chance, you get sometimes out in the extreme high or extreme low of every distribution, and that includes the sampling distribution. So you just miss a little bit. Right? But the procedure is designed so that in the long run, you're doing pretty good summaries. Right? get your estimate, plus the statistical uncertainty about it. Sometimes you can't really tell if your interval's off, but if you look at other characteristics of, and other variables, and it looked odd, this is ozone in cities, but if you're doing other health measurements, and you see in your sample, well, this group is older than average, this group is more male than female, typically, this group has more severe health concerns, they just look a little bit different. You might wonder, is this really typical of the population I'm studying? Is it kind of comparing apples to oranges, or apples to fruit juice or something, right? They could be very different. And then the interval you might suspect is a little bit funny, right? But it's hard to tell in general. So this type of interval is how things get reported in medical studies. So I was working with a colleague he's in Ohio actually, but we did something called a meta-analysis where we brought together a bunch of studies looking at gestational age, and there was whether treatment with antibiotics treated a certain condition that was associated with premature birth. And there's a bunch of studies that were done with this drug, metronidazole. And so combining all these, metronidazole versus control, sometimes it was a placebo, sometimes it was just no treatment. The main summary, and so this was a different type of model. It was a survival model or logistic regression, so more involved, bringing in more variables to explain the effects. The basic summaries were in these confidence intervals. And in this particular application, if a confidence interval includes 1, it meant no benefit, right, to taking the drug. There were other benefits, but in terms of this one outcome of prolonging pregnancy and avoiding premature birth, this particular drug, metronidazole, did not seem to make a difference, because the confidence interval represented by that line, see there's the estimate in the middle, plus or minus 2 standard errors approximately, and it's reported as these numbers over here. This one, it's 4,000 women. The interval was pretty narrow, and it included 1, which meant no effect. So this drug does not seem to do it. This was a different analysis, logistic regression to predict the probability rather than the time until birth. And again, combining all those things or breaking it out by age groups did not seem to have an effect. And again, the confidence interval was the main summary. So you go forward with this saying, we can't recommend that drug as something to do. The other drug was that was used a lot, was clindamycin. That was a little bit different. That one just barely, the confidence interval at the very upper tip, just went past 1. So again, that doesn't seem great, but maybe there was some benefit for, in some studies showed some confidence intervals that were clearly below 1. This one was below 1. These were, once we added in some more data, again, the confidence intervals included 1 and didn't show any benefit. So it kind of was used in one part to rule out, don't use that drug, don't recommend that one generally. And in this case, it basically said there's still some uncertainty about it. And if you look at it one way, it kind of looks like there's a benefit, even if it's moderate. And if you look at it another way with some dealing with missing data, a different way. But again, the summary that we can communicate for people to think about are largely in terms of these confidence intervals and some discussion around them. So it gets used in medical studies, all the time as these summaries. And it has the idea that about 95% of these intervals that you make will actually cover the truth. Some will miss slightly one way or the other. As you pull together more studies, you get very narrow one. Here's 6,000. That's the width of that one. That's really precise. This was 190 because it's a small gestational age at randomization. So it's a smaller group. We're into the study at a later time during pregnancy. And so the interval is wider because of that. These ones that had 4,000 were quite narrow, right? Very precise, because they're based on a bigger sample size. Right? And so that's the effect of standard error of 2 things. But any questions about that? That's kind of the introduction to inference, and confidence intervals. We'll talk more as we go along, but how do you get to know that standard error? How do you use 2, or do you change that multiplier in there a little bit based on small sample sizes and so on? So we'll look at a lot of variations. If you have homework 5, be sure to drop it off. And please get the pigs back so that keeps the family together. You want to work on it and bring it to my office later, that's fine. Quick change, that's fine. Thank you. What? Oh, yeah. Thank you. Thank you.
Thank you.
Thank you. Oh, the piggies, yeah. Gotta keep the farm together there.
Thanks.